Welcome back from break. Now we are going to move on to the next topic in chapter 7, which is balancing equations. In a balanced chemical equations, understand that no atoms are lost or gained, and the number of atoms on the reactant and the product are going to be equal. Now, the reason why in chemistry we need to have balanced chemical equations is because we are respecting what the law of conservation of mass indicates, okay? Which means that matter cannot be created or destroyed out of nothing. There cannot be a change in the total mass of reactant and product in an ideal situation. And the mass of the product must equal the mass of the reactants. So here we have a reaction. This is a combination reaction where we have silver combining with sulfur to make silver sulfide. And if you look at the amount of silver that we have here, this is going to be about 2 moles of silver, and we have 1 mole of sulfur, and then we're going to make 1 mole of silver sulfide. Understand that in an ideal situation, meaning if we do the reaction perfectly, the masses that we use for the reactants are going to equal to the products. Now, in chemistry, of course, there's always going to be variation because there's going to be different type of errors that occur. And depending on these type of errors, then that can affect the mass of the product that you get. But in general, we need to understand that we need to have balanced chemical equations, because the next topic that we're going to cover in this chapter is how do we do calculations taking into account that what we're working with is a reaction. So the first thing that we need to remember is how to write a balanced chemical equation. Understand that when it comes to this, when we're doing balanced chemical equations, at times I give them in words, okay? And you can see in the extra credit and in the chapter 7 homework, where you guys have instances in which your equation is given in words. In the in-class worksheet, you guys have actual practice of if the chemical formulas for the components of your chemical reaction are given versus if your reactions are in words. But please make sure that you practice if the reaction has been given in words, how actually I write those chemical formulas and I balance my chemical reaction. So these are just guidelines for how to write balanced chemical equations. You start by listing the elements on the left or the right side of the equation, meaning if you know the name of the compound, then you're going to write their chemical formulas. Then you're going to count the number of each element on the left and on the right, okay? To just make sure where do you start. And then you can only balance equations by adding large numbers in front of the compounds or elements. Because remember that if you change the subscript, you're changing the identity of your compound or element. So you cannot be balancing an equation by adding subscripts, okay? But it needs to be large numbers, which is what we call a coefficient. These large numbers in front, this is what we call the coefficient. Now, when you're adding the numbers, start with the lowest possible number, okay? And then go up 2, 3, 4, so on and so forth. If possible, aim for even numbers. It's not a set rule that you need to have even numbers always, okay? It just comes with practice, okay? And understand that the last thing that we balance in a chemical equation tends to be specifically the individual elements, okay? Let's practice how to do balanced chemical equations okay? Because it's very important that we know how to do this. So as you can see, here it says, write the chemical formula for the substance present in the reactions given, and we're going to balance them, okay? So let's go through problem number 1 together to make sure that people know how to do these problems for the upcoming exam. So here we even have the state of matter given for the compounds that are present in these reactions, okay? So for example, in the first one, it says solid potassium oxide, okay? So if we have solid potassium oxide, the chemical formula for it is going to be K2O. To illustrate that it is solid, we're going to put an S, okay, next to the chemical formula. Then we have water. Water is H2O. That is found in liquid form, so we put an L and we put it in parentheses next to the water. That is going to come together and form potassium hydroxide, and potassium hydroxide is KOH, okay? So, and this is in solid form. So this is our general reaction, okay? Now, understand that now we need to take into account how many atoms we have of each, okay, on the reactants and in the products. So I'm going to put R for reactants, P for products, and I'm going to put the atoms that I have, which is potassium, oxygen, and hydrogen, okay? In the reactants, I have 2 potassiums, I have 2 oxygens, and I have 2 hydrogens. For those students that are wondering where I got these numbers from, look, we have 2 of the potassiums. That's where I got that. We have an oxygen here, and we have an oxygen here. Those are my 2 oxygens. Here I have an H2O, 2 hydrogens. Then, if we look at what happened in the products, okay, we have 1 of each. We have 1 potassium, 1 oxygen, 1 hydrogen, okay? So we are going to no, that's just, thank you for answering in the chat. The symbols in the bottom right corner of the chemical formulas, those are just the state of matter. That's where they're placed. So we can see here that here's the subscript of 1, subscript of 1, subscript of 1. That's where these ones come from. So again, in order to balance an equation, excellent, already the answer is in the chat. We need to put a coefficient in front of the whole compound. So in this case, if I put a 2 in front of potassium hydroxide, when this 2 gets distributed, or in other words, multiplied by the 1, then now I have 2 atoms, okay, of each of these. And as you can see, now I have the same number of atoms in the reactants and the products, okay? Let's do number 2 together. I have solid aluminum. Excellent. So I'm going to put Al in solid form. If I have the word oxygen, if I have the word oxygen gas, if I have the word molecular oxygen, all of that has the same chemical formula. What would it be? Excellent. O2. So remember, if we have a plain oxygen, if we have the word molecular oxygen, or we have oxygen gas, that means O2. And remember, whenever we have in a reaction any of your diatomic molecules, it's going to show up as a diatomic molecule, okay? So don't be confused by that. And then we have aluminum oxide. So what is the chemical formula for aluminum oxide? Excellent job. It's going to be Al2O3. This is why it's very important, you guys, that you can go from words to chemical formulas. You can see we're going to see it throughout this week for the exam. So if we do a similar table, okay, trying to determine what's happening to the elements in the reactants versus the products. I'm only dealing with aluminum and oxygen. What's happening in the reactants versus what's happening in the products, okay? So how many aluminums do I have in the reactants in the beginning? Great job. How many oxygens? Excellent. When I look in the products, how many aluminums do I have? Great. And how many oxygens? Excellent. You guys know how to count your atoms. Amazing. Now, I need to make sure, because nothing matches, right? That I need to at least balance something, right? Now, we never start by the single elements, okay? We never start there. So we should start by at least putting a coefficient in front of the compound, okay? So we can balance this equation. So if I put a coefficient of 2, that's going to take my aluminums to 4, and it's going to take my oxygens to 6. I'm still not balanced yet. But now that I know that I have those atoms in the product, okay? And since I only have one aluminum in the reactant, what coefficient can I put on the aluminum? Excellent, of 4. That will take my aluminums in the reactants to 4. So I know that I have 6 oxygens in the product. So what coefficient can I multiply by 2 to give the reactant those 6 oxygen atoms? Excellent job. A 3. That will take this to 6. So in this reaction, we have a coefficient of 4, followed by a coefficient of 3, followed by a coefficient of 2. To be honest with you guys, when it comes to balancing equations, practice, because that's the best way that you can solidify that knowledge. Make sure that you practice, okay? Put a 1 in the chat if you want to do at least one more. Excellent. So I'm going to give you guys 2 minutes to do number 3, okay? So I'll give you 2 minutes to do number 3. Okay, let's write the chemical formulas for each of the components of this reaction, starting with sodium peroxide. That is Na2O2. We're going to react that, oh, and that is aqueous, so that's AQ. We're going to react that with water, which is H2O, and L for that liquid. In terms of the product, we're going to do NaOH, also in aqueous form, and the oxygen gas is diatomic, so it's O2 in gas form. Okay, put a 2 in the chat if at least you could write all the components of the chemical formula. Let me see that people are able to get at least that far. Great. Let me just erase the bottom example so we can look at the work for this one here. So when we look at the number of atoms of each of the elements in the reactants, we have sodium, we have oxygen, and we have hydrogen. We need to have the same elements on the other side. Because remember, in these reactions, we don't have oh, there's a question in the chat. Why OH minus is not there for hydroxide? Because remember that hydroxide in this case is paired with sodium. There are an ionic compound, so it's Na plus OH minus, so that cancels each other and it doesn't have a charge in the corner. No problem. Excellent. So when we look at the reactant versus the product, we see that we have 2 sodiums, 3 oxygens, 2 hydrogens. In the product, we have 1 sodium, 3 oxygens, 1 hydrogen. Okay. Now, the thing is that when we look at this, we can look and say, oh, the oxygens look balanced. Okay. Because we have 3 in the reactants and 3 in the products. So technically, the only thing that we have to balance is the sodium and the hydrogen. But if we pay attention closely of the sodium and the hydrogen in the product, that is also going to affect the count for oxygen, because in the product, we have oxygen in a compound where sodium and hydrogen is, okay? So at first, we need to try to balance, okay? Okay, at least the, one of the 2 that we have unbalanced. We have sodium and we have hydrogen. So we can say, okay, let me balance those 2. So if I put a 2 here, then that would be that my sodium goes to 2, my hydrogen goes to 2, and all of a sudden you're like, oh, yay, those are 2 balanced. But by putting a 2 in the front of that NaOH, what happened to the oxygens? How many oxygens do we have in the product now? Excellent, we got 4. So now your sodiums are balanced, your hydrogens are balanced, but your oxygens are not balanced. So we need to try to balance our oxygens, okay? Now, if we put a 2 in front of the water to try to balance the oxygens, then we will have 2 oxygens from the that are within the water, and we have the 2 oxygens in the sodium peroxide, so that will take to 4. But then putting a coefficient of 2 in front of the water, then what happens to the hydrogen, you guys? Excellent, it became 4. So then that means that that coefficient of 2 in front of the sodium hydroxide really doesn't make any sense. okay? Now, if we put a coefficient to balance the hydrogens, meaning that I move this to a 4, oh, my hydrogens go to 4. Great, I balance them. But now my oxygens go to what number? How many oxygens we have in the product now? Excellent, we have 6. How many sodiums do we get now? How many sodiums we have in the product? Excellent, we have 4. But notice, okay, that the two things that are unbalanced in between reactant and product, which is sodium and oxygen, in the reactant, we have them together, okay? So if we put a coefficient of 2 before the sodium peroxide, we take our sodiums to 4. Now our oxygens, 2 times 2, there's 4 oxygens plus the 2 that come in the water, the oxygens become 6. And then the hydrogens remain the same. Now we have the same number of atoms in the reactant and the product. So understand that, again, balancing equations is going to take time, is going to take practice, okay? So make sure that you know how to do these problems. One thing that I didn't state before, but I'm just going to say it now. For example, in this reaction, since oxygen gas didn't get a coefficient, it does have a coefficient. It has a coefficient of 1. So similar to the potassium oxide in the water that has a coefficient of 1. It's not a coefficient of 0, it's a coefficient of 1. So if we don't put any coefficient to any portion of my molecule, of my chemical reaction, it has a coefficient of 1. Any questions when it comes to balancing equations? Excellent. Since there are no questions, now that we know how to determine reactions, we know how to balance them, we know how to classify them, let's look at the concept of chemical quantities in reactions, okay? So as you can see here, we have a reaction that establishes that we have iron combining or reacting with sulfur, making iron 3 sulfide. To balance this equation, we needed to put 2 in front of the iron, 3 in front of the sulfur, and then, even though it's not written, you can see that there's a 1 in front of the iron 3 sulfide. Now, why is this important? Because a chemical reaction, we can always read it, okay? And as you can see here, if we try to read this reaction, it's going to say 2 moles of iron plus 3 moles of sulfur produce, create, make as a product 1 mole of iron 3 sulfide, okay? So when we are comparing chemical quantities in a reaction, understand that these coefficients that we have in a balanced chemical reaction can be utilized as conversion factors. And we can relate any 2 portions of any reaction to each other. So as you can see in the bottom, we are placing as a fraction, okay, the different relationships of the components of this reaction. So for example, in the first one, we have iron and sulfur. So we are relating 2 reactants in the reaction. So 2 moles of iron, you see, over 3 moles of sulfur. All this means is that in my chemical equation, these 2 quantities are going to be related to each other based on my balanced chemical equation, okay? You can see, you can relate the reactants to the product. So in the second one, we have iron related to how much product in moles are we going to make. And you can see that the relationship is 2 to 1 or 1 to 2, depending on what we're trying to discover. And lastly, we have the other reactant related to the product. And based on my balanced chemical equation, I see the relationship between sulfur and my product, okay? So remember, we can utilize the coefficients in my balanced chemical equations as conversion factors if I'm trying to relate different components of a chemical reaction, okay? So that takes me to the calculations that we need to be familiar with when it comes to chemical reactions. As you can see, this calculation is for relating two components of a chemical reaction, okay? Substance A and substance B. What is substance A and substance B? Whatever the question is asking you to relate, okay? So substance A can be a reactant, substance A can be a product, substance B can be a reactant, substance B can be a product. It is not determined that substance A needs to be a reactant or substance B needs to be the product, because in chemical reactions, we can relate two components overall, okay? So as you can see here, you guys need to be familiar how to convert the following. If you are given moles of one substance and find moles of another substance, your conversion factor is going to be the mole to mole factor, okay? Where we get the mole to mole factor is going to be the coefficient in the balanced chemical equation. Okay? Molar mass is going to be our vehicle in order to transform. If we're giving grams of something, to convert it to moles. Okay? So as you can see, this flow chart gives you how to convert between different amounts in a chemical reaction. Doesn't matter if you start with moles or start with grams. You can utilize this flow chart. So let's actually do an example. Okay? This is a calculation in which we are relating two things in a chemical reaction in terms of moles. So we're going to use the mole to mole factors. As I mentioned to you guys a few moments ago, but let me rewrite it here. Where do I get that mole to mole factor? The coefficients in the balanced chemical equation. The problem reads, how many moles of iron 3 oxide can form from 6.0 moles of O2? In these, you are always going to assume that you have enough of the other reactant in order to make that product, okay? So we're going to write the value that was given to us, which is 6.0 moles of O2. Then I'm going to use my conversion factor, which is the mole to mole factor. So I'm relating O2, okay, to the product. So I know that 3 moles of O2, okay, based on my balanced chemical equation, are related to 2 moles of iron 3 oxide. Okay? So when I do this, I'm going to take 6.0 times 2 divided by 3, okay? So your calculator display shows a 4, but how many sig figs, you guys? Again, the sig figs are going to hunt us. Excellent, 2 sig figs. So even though your calculator display shows you a value of 4, the correct answer is going to be 4.0 moles of Fe2O3. Because remember, we're going to be using dimensional analysis. Moles of O2 cancels with moles of O2. Okay? Another important calculation that you guys need to know how to do is transitions from mass of one substance to mass of another substance. We have the following reaction. Molecular nitrogen reacts with molecular hydrogen to form ammonia. Okay? So, as you can see here, suppose we want to determine the mass in grams of ammonia that can be produced from 32 grams of molecular nitrogen in the following equation. We are going to assume that we have enough molecular hydrogen to react all of that molecular nitrogen. So when we are doing these transitions, because we're going from mass to mass, this is what is given. This is what is needed. Whenever you have to do this conversion, you need 1, 2, 3 conversion factors. Okay? Let's get started when it comes to this. Let's write down what is given to us. 32 grams of N2. So in that first step, I'm going to divide by the molar mass of my compound. So in the top, I say 1 mole of N2. What's going to be the mass of N2? You see that people remember how to do that. How do we determine the mass of N2? Let me see if you guys get the same thing I got. Just put in the calculator, mass of N2. This is finding the molar mass of a compound. We learned how to do that last week. Excellent, that's what I also got. 28.0134 grams of N2, okay? We're done with this conversion. Next one, I'm going to use the coefficients in my balanced chemical equation to relate the 2 different compounds that I'm interested in. So I have N2 and ammonia. So it's moles of ammonia, moles of N2. How many moles of ammonia do I have in my balanced chemical equation? Let's put it in the chat. How many moles of ammonia do I have in my balanced chemical equation? Great job. 2. How many moles of N2 do I have in my balanced chemical equation? Excellent job. Now, one more piece to get to the final. We need to find the molar mass of that needed compound. So I'm going to put in the bottom 1 mole of NH3. And then on top, I'm going to put the molar mass of NH3. Calculate the molar mass of NH3. I'm going to do it on here too. Let's see if we get the same thing. Molar mass of ammonia. Excellent. That's what I got also. 17.03052. When it comes to canceling units, grams of N2, grams of N2, moles of N2, moles of N2, moles of ammonia with moles of ammonia. So my final answer is in grams of ammonia, okay? So I'm going to take 32 times 1 times 2 times 17.03052. And then I'm going to divide the whole thing by 28.0134 times 1, which is just the first value. And I need to round to 2 sig figs because that's where we started. Excellent. That's what I got also. $39 grams of ammonia. So again, this flow chart for knowing the calculations can help you determine where do I start? So in other words, what is given to me and where do I need to go? Meaning, okay, where is where I will stop in terms of my calculations. So taking that into consideration, there is one practice problem. These type of problems in chemistry are called stoichiometry, okay? So this is the problem that is in the in-class worksheet, okay? The first thing that we have to do is generate the balanced chemical equation. So here we have calcium chlorate reacted with calcium chloride and oxygen, okay? So I'm going to give you guys a minute for you to write the balanced chemical equation. To write the balanced chemical equation. Just as a review, what kind of reaction is this? What is the classification of this reaction? What is the classification of this reaction? Any guesses? Classification of this reaction. Thank you, Daniela. Excellent. Decomposition. This is a decomposition. Okay? Because we have one thing turning into two things. Okay. So for this balanced chemical equation, let's write our reactant, which is CaClO3. And this decomposes to CaCl2. And again, if we have oxygen in the reaction, we are referring to O2. So just putting the letter O will be incorrect. Okay? So to balance this reaction, we can see that we have calcium, we have chlorine, we have oxygen, calcium, chlorine, oxygen. We have 1 calcium, 2 chlorines, 6 oxygens, 1 calcium, 2 chlorines, 2 oxygens, okay? So our calcium and our chlorine is balanced. And since the oxygen is just the difference between the two, we only have to put a coefficient in front of the O2. What is that coefficient that we put in front of the O2? Excellent. A coefficient of 3. We didn't write a coefficient before the calcium chlorate and the calcium chloride, but they have a coefficient. The coefficient that they have is a value of 1, okay? Put a 1 in the chat if at least question 1 makes sense. Let me make sure that everybody at least understands what we did in the work for number 1. Excellent, okay? Let's go through the calculations. In the first calculation, it says how many moles of oxygen will be formed if 2.84 moles of calcium chlorate decomposed. So here we are given moles of something. In this case, moles of calcium chlorate. What we need is moles of something else in our balance equation, okay? It's going to be moles of the oxygen atoms, okay? Or the molecular oxygen, sorry. So we're gonna write down what is given to us, which is 2.84 moles of CaClO3 To convert this to moles of oxygen, we're going to use our conversion factor, which is the mole to mole ratio. Because I need to cancel the moles of CaClO3, that's what I put here. And then on top, what is needed, which is going to be moles of oxygen, okay? So what is the value of in the top of my fraction? Excellent, a 3. What is the value that goes in the bottom of my fraction? Great job. Oh, you guys are going to make me so proud this weekend with this exam. I'm going to celebrate 4th of July. Very happy with you guys' accomplishments. So when I take 2.84 times 3 and I round it to 366, what do I get? Excellent. That's what I got also. Okay. Any questions about problem number 2? Then let's move on to problem number 3. Okay. Understand that problem number 3, you guys do not have examples like this in the textbook. You do have examples of similar problems when it comes to calculations like number 2 and number 4, but the calculation number 3 is not in the textbook, okay? Just wanted to warn you. So when we look at problem number 3, as you can see, it reads, how many grams of calcium chloride will be formed if 1.93 moles of calcium chlorate decompose? So we're trying to see how much product we're going to form if we start with 1.93 moles of calcium chlorate. So we have to write what is given and what is needed. What is given is moles of one substance. What is needed is grams of another. Okay. So for this one, we need to use two different conversion factors. So let's write what is given to us, 1.93 moles of calcium chloride I know I need two conversion factors. Okay. The first conversion factor, okay, is based on the balanced chemical equation. So I need moles of CaCl2 on top, moles of CaClO3 in the bottom. So what's the relationship, you guys, between these two molar amounts in terms of our balanced chemical equation? What's the relationship? Great job, 1 to 1. Now, in the last step, we're going to say 1 mole of CaCl2 corresponds to grams of CaCl2. So we need to calculate the molar mass of CaCl2. Oh, it's just that my pen, it happens sometimes. There you go. Like it does a separate stroke. Excellent. So I got to run that. It's 110.0, not 0. 110.984 grams. That's what I got. Okay. So when I look at my unit cancellation, moles, 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 they all cancel each other. So then my answer, rounded to 3 sig figs. Excellent. That's what I got also. 214 grams of CaCl2. Okay. Any questions about problem 3? There's a question in the chat. How did I get the grams? That is the molar mass of my second substance. Look at your conversion factors. Moles of A is going to be the moles that are given, which is calcium chlorate. The mole to mole factor comes from the balanced chemical equation. So in the second conversion factor, I need the molar mass of that second substance to get to the product, to get to the correct answer. So the grams of the calcium chloride come from the molar mass of it. I'm going to give you guys 2 minutes to do number 4. In number 4, we are given mass of one substance. We need to find grams of another substance. So we have 1, 3 conversion factors that we need in order to go from grams to grams. So I'll give you guys 2 minutes. Okay, let's go over the answer. So for this one, we're going to write what is given to us, which is 3.36 grams of calcium chloride, CaCl2. Then we have 3 conversion factors. So we have 3 fractions. In the first one, I'm going to do the molar mass of that first compound, which is calcium chloride. And we already determined the molar mass of calcium chloride in the previous example. So we're going to do 110.984 grams for CaCl2. And then we're going to do 1 mole of CaCl2 on top. In the next one, we're going to do the mole to mole factor, okay? Remember that the mole to mole factor comes from the coefficients in the balanced chemical equation. And here we're relating calcium chloride to calcium chloride. So in the bottom, we're going to do mole of CaCl2. On the top, mole of CaClO3, 2. And we already know that the relationship between them is 1 to 1. Lastly, we are going to multiply by the molar mass of CaClO3, 2. So we put in the bottom moles of CaClO3, 2. And on top, we have to put the molar mass of this compound, CaClO3, 2. So to calculate molar mass, just as a review, we have calcium, we have chlorine, we have oxygen. We have 1 calcium, we have 2 chlorines, and we have 6 oxygens. Okay? We're going to multiply this by the molar mass of each of these. Calcium is 40.078. Chlorine is 35.453. And oxygen is 15.9994. We're going to do the multiplication, and then from there, we're going to add them. So let me do it in my end. Try it at home. 40.078 plus 2 times 35.453. What molar mass did you guys get? There's a question in the chat. The mole ratio was obtained from the balanced chemical equation. Correct. So in order for you to do this, again, for whenever we have chemical quantity in reactions, remember that we're looking at the coefficient in the balanced chemical equation. Always. That's where we get the mole to mole ratio. Excellent. That's what I got also. 206.9804 grams per mole. We already put the mole in the bottom. So in the top is 206.9804. We're going to multiply that times times 1 times 1 times 3.36. And we're going to divide the whole thing by 110.984. Excellent. We need to round it to 3 sig figs. Grams, moles with moles, moles with moles. So in terms of space, this is going to be 6.27 grams of CaClO3. Okay. Any question about stoichiometry problems, which means we are looking at quantities in a chemical reaction? Make sure that you get practice by utilizing the textbook problems. We have some problems in the homework. We have a problem like this in the extra credit also, okay? Excellent. Since there are no questions, let's proceed to the last topic in chapter 7, which is the energy in chemical reactions, okay? Understand that when a chemical reaction happens, you guys, it's not all random, okay? We need certain conditions that need to be met in order for this reaction to work. The first condition is going to be collisions. The two reactants must meet each other. In other words, collide. They need to be bumping into each other. Now, in terms of the orientation, these reactants understand that they need to do it in a correct alignment, because we need to break bonds and we need to form bonds. Now, also, we need to do this with a particular amount of energy. The collision, okay, of this reactant must provide enough energy of activation, okay? So energy of activation, or in other words, activation energy, is going to be that energy barrier, that mountain that you see here, that the reactants have to overcome in order to get to products. okay? All of this, we are going to illustrate in what is called an energy diagram. So we can see here that we have the reactants, and what we are actually plotting is, when it says energy consumed or energy released, is going to be the potential energy that is present in the bonds for these different compounds, okay? So at first we have the energy of the reactants, or the potential energy that are present in those bonds. Then the activation energy, again, is going to be the energy barrier that we have to overcome to get to products. This reaction specifically, along with how conversion is happening, is going to release energy, which takes us to the different types of energies that we find in chemical reactions. So the example on the previous slide, it is also what has been illustrated in the energy diagram that we have on the left side of the slide. This is what is called an exothermic reaction. If we have an exothermic reaction, like the name implies, exo meaning exit, thermic is going to be that energy. In an exothermic reaction, heat is going to be released, okay? So you can see here that overall, the energy of the products, because when we plot this, in the y-axis, energy is increasing. That is, numbers are increasing as we go up. That's why the orange arrow. Understand that the energy of the products is less than the energy of the reactants, okay? And when we have an exothermic reaction, heat is going to be in the product. So you can see here that we have the example of carbon reacting with molecular hydrogen to make methane. This reaction is an exothermic reaction, and since heat is being generated, you can see the energy units in the product of the reaction. Now, even though there's some reactions that are exothermic, other reactions are actually endothermic. Then you can see the energy diagram for an endothermic reaction on the right side of the slide, okay? So in an endothermic reaction, energy is absorbed from the environment into the reaction, okay? So here, energy needs to be put into the reactants, okay? So understand that instead of heat being released in an endothermic process, heat is being absorbed. Okay. When we look at the energy, again, the potential energy in the bonds for the products versus the reactants, when we have an endothermic process, the energy of the products is going to be higher than the energy of the reactants. Okay. And since heat is being absorbed and it is present in the reactant, you can see units of energy in the reactant when we have an endothermic process. Now, understand that so far, since we've been talking about chemical reactions, we have not talked about the rate of the reaction, okay? The rate of the reaction, okay, is a measure of the changing concentration of the reactants or the changing concentration of the products per unit time. That's what the rate of the reaction is. So let's understand that whenever we're looking at the rate of the reaction, okay, that's changing concentration from reactant to product, there are factors that actually increase the rate of the reaction. They are summarized in table 7.4 in the textbook. So you need this table for exam 2. Okay, so as you can see, increasing the reactants, okay, the concentration of them actually increases the rate of the reaction, because if you have more reactants present in your reaction, there's more collisions that actually happen. Increasing the temperature of your reaction, okay, proceeds to make more collisions, okay, and these collisions are going to generate enough activation energy that then we can actually speed the reactions. The last way that we can actually increase the rate of the reaction is by adding a catalyst, okay? And what a catalyst does is that it lowers the activation energy, okay, for your reaction. So on the left side of the slide, we have an energy diagram specifically for if I have a reaction that is not catalyzed versus a reaction that is catalyzed, what is the difference, okay? So there is an overlap between the reaction without a catalyst with catalyst. So I'm just going to use my highlighter tool to just introduce a line here. And then there's an overlap here, so we know that line is there. So the turquoise line actually is representing what is the reaction progress of a reaction without a catalyst, okay? As you can see, we can see the hill that is really large. Now, the addition of catalyst to the same reaction, as you can see now, we have a smaller hill to climb to get to the product, okay? So a catalyst not only increases the rate of the reaction, but it does it by lowering the activation energy. And out of the different factors that I have mentioned so far, this feature of lowering the activation energy only is present in catalyst. When it comes to catalysts, we're going to learn in this class that catalysts can be molecules, but it can also be biomolecules. So towards the end of this semester, we're going to learn how we have biological molecules that act as catalysts, just because all the reactions that are happening in the body have to happen in an increased rate state. So understand that the body has actually designed these biomolecules, which if you have taken physiology, you understand the concept of enzymes, or if you have taken biology. So an enzyme is a catalyst, but then in our body, that catalyzes most of the reactions that happen, okay? Now, one thing that I need to mention is that there are two important things when it comes to a catalyst. On the third bullet point, it says that it's not used up in the reaction. What I mean that is not being used up is just that the catalyst creates the lowering of the activation energy, but at the end of the reaction, you regenerate that catalyst. So what I mean that is not used up is that the catalyst is regenerated at the end of the reaction. So it can keep on doing its job, okay, with new reactant molecules. The other interesting thing, and the reason why we have that overlap in the energy diagram, is that the use of a catalyst does not change the potential energy of the reactants or the products. It literally just lowers the activation energy. So the energy of the bonds in the reactants, or the energy of the bonds in the products, is not affected. In order to understand catalysts, I use the analogy of when you're running a race, okay? Especially if you have done Spartan races and all of this awesome, different races that are out there. Has anybody done a Spartan race? Put a 1 in the chat, or put a 1 in the chat if you have heard of these running races. Okay, only one person. People haven't heard of Spartan races. Even if you look in social media, sometimes they put them. So when it comes to Oh, there you go. Great job, Yesenia. Awesome. When it comes to these races, you have to, at some point in the race, and I think it's typically towards the end, there's a big wall that you need to climb, okay? So what a catalyst does is that it's kind of like, it helps you, okay, climb that wall, but it's going to be now a lower wall, okay? No, it's different from hitting the wall in a marathon, because you're not gonna hit it. This is going to be like you get a VIP pass, and then instead of climbing like a 6-foot wall, then you are like, but I have my ticket, because my catalyst is going to lower my wall. So it's kind of like my wall is going to be smaller. Because I think when you're hitting the wall in a marathon, it's more along the lines that at that point is when everything slows down. And remember that we are increasing the rate of the reaction. So technically it is, I don't know, the marathon analogy may not work with hitting the wall. But I think if you think about it of like, all of a sudden your wall gets smaller, okay, by the use of a catalyst, you can still reach the end point. Or actually, when I did my half marathon about 3 weeks ago in San Diego, like I saw around mile 10 how there's this bus. I don't know if anybody has done the rock and roll, or they've done a half or a full marathon. There's this bus that can pick you up if you just say like, I'm not going to complete this, and it takes you to the end. So just imagine that bus is going to be your catalyst, because you still finish the race, but then you don't have to, climb the wall. The bus is going to take you to the end point. Okay. Any questions when it comes to the factors that affect the reaction rate? Excellent. Since there are no questions right now, I'm going to stop recording.